Now we're able to focus on buffer strength and buffer range. So buffer capacity is going to allow us to understand the strength of a buffer. And it depends on two things: the concentration of the buffer components and how close those component concentrations are to one another. So for example, let's say that we have our pH here, and our initial pH is going to be 4.74. And then we have an increase in pH as we go from left to right. This is a bar graph. And on here, on our y-axis, we have concentrations of buffer components. So we have a very high concentration of buffer components, which is 1.0 molar. And then we say we have a low concentration of buffer components, which is 0.030. So if we add a strong base to these buffer solutions at all these different concentrations, then we're going to be able to see the results of how this particular buffer at that concentration is able to resist change. So when you look at the low concentration buffer here of 0.030, this low buffer solution here, guess what? The ability to resist pH was not that great. As you can see, the pH has increased. But when we have a high concentration of our buffer components here, the ability to resist pH is really, really good. As you can see, it's still around 4.74, which is going to be our initial amount. So that strength is going to be dependent on that concentration of those buffer components. And again, the other aspect of this is being able to compare and contrast those buffer components. So for example, if our conjugate base and our weak acid are the initial amounts are both equal to 1.00, then the ratio of the buffer components is also equal to 1.00. But if we change the amounts, say this is now equal to 0.75 and this is now equal to 3.75, just for example, then the ratio, which is the 0.75 divided by 3.75, is now 0.2. So of course, way off from being close to 1. We want to be able to be as close to 1 as possible, or for our ratio to be equal to 1, meaning that our buffer components are also equal to 1 individually. And so again, for buffer capacity and strength, you want to say that you have really high concentrations of the buffer components, and you want your buffer component to be equal or be as close to equal to 1 so that you get the best and highest buffer capacity. Now, let's focus on buffer range, okay? And the buffer range is simply the pH range where the buffer is effective. And so how do we figure out if a buffer is going to be effective? Well, we relate it to the ratio of buffer components. And so we're still dealing with the ratio of buffer components, and we still want that ratio to be as close to 1 as possible. And let's talk about why by going to the extreme. So if we want our ratio to be close to 1, let's talk about when it's not 1. So if our ratio is not 1, say we increase the amount of our conjugate base here, what's going to happen? We can use the Henderson-Hasselbalch equation and see how it affects our pH, just like we saw before. Well, what's going to happen is that now our ratio is going to be larger. It's going to be 10, which is not close to 1, right? And so we're going to have pKa plus log of 10 over 1, for example, and that's going to be pKa plus 1. So as you can see, our pH is going to increase because we have increased our buffer amount, and therefore it's going to decrease our H3O plus amount, and that's what we will see here. On the other hand, if you had another buffer with that same ratio, except instead of having a large amount of our conjugate base, we had a large amount of our weak acid, then it's like having 1 divided by 10 here. And so what's going to happen? You're going to have pKa plus log of a negative number, and our pH is going to decrease. If our pH decreases, it's going to be an increase in H3O plus. And if you're trying to use our buffer range with these values, then you can see that one concentration of one component is more than 10 times the concentration of the other. And so the buffering action is going to be very, very poor. So then the question becomes, what is an effective buffer range? An effective buffer range is going to be plus or minus 1 pH unit of the pKa in the acid component. So we want to say pH is equal to pKa plus or minus 1. Nothing above it, nothing less. Okay, folks? That is how we're going to be able to get an effective buffer range. Let's get to the Avengers compound for an example. All right, it states the molecular scenes below, which are these scenes here, 1 through 4, represent samples of 4 ratios, components, and that's what I see here. As soon as I see HA divided by A minus, I start thinking ratio of the buffers or components of the buffer, okay? And so this ratio is going to be HA divided by A minus. That's if we specifically want to relate it to H3O plus. But of course, we flip this when we want to relate it directly to pH using the Henderson-Hasselbalch equation, okay? It also tells us that the weak acid is blue and green, and the conjugate base is green on its own, and the other ions in water are not shown. So when it's basically green like this, that's going to be the conjugate base, and when you have blue and green, that represents our weak acid, and the blue is going to represent our proton. They want us to know which buffer has the highest pH, just based off these molecular scenes. Which buffer has the greatest capacity, just based off these scenes. And should we add a small amount of concentrated strong acid or strong base to convert sample 1 to sample 2, assuming no volume changes? So this is how we're going to be able to answer and approach this question. So the first thing I did is go ahead and write my Henderson-Hasselbalch equation just in case I have to use it. And then the second thing I did is went ahead and counted the numbers of each of my weak acid and my conjugate base in my molecular model here. So I have 3 of my conjugate bases here and 3 weak acids, 2 conjugate bases here and 4 weak acids, 4 of my conjugate base and 4 of my weak acid here, and then 4 of my conjugate base and 2 of my weak acid here. Why am I going ahead and get this? Because I want to go ahead and figure out my ratio. If I figure out my ratio of A minus HA, I can directly relate that to my pH. Not only can I use this ratio for my pH, I also can use it for my buffer capacity as well, because we can look at concentration. And so what I'm going to do here is just go ahead and get all of my ratios, which is going to be my conjugate base divided by my weak acid. So for scenario 1, I have a ratio that equals to 1, because I just took 3 divided by 3. Here I take my conjugate base divided by my weak acid, so that's 2 divided by 4. I get 0.5 here. I get 1 here, and I get 2 here. When they ask me which buffer has the highest pH, they're essentially asking me which sample would be considered the most basic, okay? Because if you're going to have a high pH, that means you're going to be considered probably a basic solution, okay? And so that also means I'm going to have probably more of my conjugate base because I'm dealing with a basic solution. So I'm looking here, I'm like, okay, I have 3 here, but it's equal to my HA ratio, so that's not going to work. This one's also equal to 1, that's not going to work. We only have scenarios 2 and 4 to look at for letter A. Which one's going to have the highest pH? Well, the one with the highest pH is going to be the one with the most conjugate base, and of course with the highest ratio, which is going to equal 2. Because we're increasing the numerator here, then that means we have to also increase our pH as well. And so for letter A, the molecular scene that's going to show the highest pH would be number 4. For the next part, they ask for which buffer has the greatest capacity. Okay, so what is capacity going to depend on? It's going to depend on the ratio. We want the ratio to be closest to what? Closest to 1. And it's also going to depend on what? The concentration of the buffer components. So automatically, we're looking for our ratio to equal to 1. That's going to be molecular scene 1 and molecular scene number 3. So the question becomes, which one do you choose? You're going to choose the one with the highest concentration. The highest concentration is going to be the one with the highest numbers. So the molecular scene that has the greatest capacity is going to be scene number 3. We got letter A and we got letter B. Let's go ahead to letter C. Should we add a small amount of concentrated strong acid or strong base to convert sample 1 to sample 2, assuming no volume changes? So they want us to figure out, okay, we're going from something that's very close to 1 to now they want us to convert it to a sample that's close to 0.5. Okay, and they want us to figure out how do we do this. I automatically look at my ratios. As we can see, sample 2 has a lower ratio than sample 1. So in order to convert sample 1 to sample 2, we need to decrease the amount of the conjugate base and increase the amount of the weak acid. So how do we do that? Well, it's all about the ratio. So I'm going to focus on sample 1 because that's what they want us to convert. Sample 2, as we see, is going to be lower than sample 1. So the question becomes, if I add acid to sample 1 or if I add base to sample 1, is that going to increase or decrease my ratio? Now we know in order to go from sample 1 to sample 2, we have to effectively decrease our ratio. So let's talk about it. If I add acid, that means the conjugate base in my ratio is going to use up that acid to get back to equilibrium, right? So if I effectively decrease my conjugate base, and I'm going to end up increasing the weak acid that's formed. And so my overall ratio is going to decrease, which is what we're looking for, right? And so that means in order to convert sample 1 to sample 2, we should all add a small amount of concentrated strong acid. Now let's go ahead and read the base portion anyway, just so we can understand. If we add base to sample 1, then what's going to happen? Our weak acid is going to use up the base. And so our ratio is going to increase. And so that means you're going to have more conjugate base. And so therefore our ratio increases to a number that's higher than sample number 2. And so that's not what we're looking for. It's definitely going to be better to add that strong acid. And so that is letter C. And this is how I kind of get through connecting Henderson-Hasselbalch and buffers, what we know thus far. Okay, so I'm going to add acid to this. Let's get on to the next concept, folks.